origins of deep learning lie in the perseverance of researchers like Geoffrey Hinton, Joshua Bengio, and Jan LeCun. These scientists pursued neural networks long after most of their peers had abandoned them. In the 1980s and 1990s, the dominant approaches in machine learning were more mathematical and less biologically inspired. Decision trees, support vector machines, kernel methods. They were considered cleaner, more efficient, and easier to train. Neural networks, by contrast, seemed clumsy and computationally demanding. Data was scarce, computers were slow, and many concluded that the brain inspired analogy had no future. But Hinton and his collaborators saw potential. They believed that if networks were made deep, stacked with many layers, the system could gradually transform raw input into high level features, mirroring the hierarchy of perception in humans. They spent decades refining ideas, publishing papers, and enduring skepticism until finally the rise of big data and powerful GPUs made their vision practical. To understand what makes deep learning so revolutionary, it helps to start simple. Imagine predicting the height of a child based on their age. If we collect enough examples of ages and corresponding heights, we can draw a curve that connects them. That curve represents a model. It takes an input, the age, and produces an output, the height. Training the model means adjusting the curve until it fits the examples as closely as possible. This is the essence of supervised learning, where labeled data, pairs of input and output, guide the model. If the input is a photo of a dog and the output is the label dog, the model gradually learns the mapping between pixels and categories. Supervised learning has driven much of deep learning success because with enough labeled data, neural networks can discover patterns that humans might miss. Traditional or shallow networks contained only a single hidden layer between inputs and outputs. These could approximate many functions, but only with an impractically large number of units. Deep networks overcame this by stacking multiple layers, each transforming the input in increasingly abstract ways. Consider how we humans perceive images. We don't recognize a face all at once. First, we perceive edges, then shapes, then arrangements of features, and finally, the identity of the person. Deep networks function similarly. The early layers detect simple patterns like edges. Later layers combine these into shapes and eventually into whole objects. This hierarchical structure allows deep networks to capture relationships that shallow ones cannot. The outputs of deep networks are not limited to a single prediction. They can be structured, complex, and high dimensional. In computer vision, for example, a network may not just label an image as containing a cow, but can assign a label to every single pixel, distinguishing the cow from the grass and sky. This task, called semantic segmentation, demonstrates the ability of deep learning to handle fine grained structure. Another example is depth estimation, where the model predicts how far away every pixel in a street scene is. The output is not just a single number, but an entire depth map that reconstructs the three dimensional world. These capabilities make deep learning especially powerful for tasks where the outputs mirror the structure of the inputs. Generative models take the story further. Instead of just recognizing or labeling, they create. By learning patterns hidden in data, they can produce entirely new examples. Images of human faces that don't belong to real people, passages of text that read as if a person wrote them, or pieces of music in the style of great composers. What makes them particularly clever is their use of latent variables, abstract representations of what underlies the data. If we want to generate an image from a caption, for example, we don't need a massive dataset of text image pairs. Instead, we can map the text into latent variables, map images into latent variables, and then learn the relationship between the two. This reduces complexity, improves plausibility, and even allows for diversity. The same caption might yield multiple different but equally realistic images. Generative models are already transforming industries, fueling creativity, and raising important questions about authenticity in the digital age. Reinforcement learning represents another major pillar of deep learning. Unlike supervised learning, which relies on labeled examples, reinforcement learning places an agent in an environment where it must act, learn from rewards, and improve over time. The catch is that rewards are often delayed. Imagine a robot navigating an obstacle course. It may only receive a reward after reaching a checkpoint, but dozens of movements contribute to that success. Determining which actions were responsible is called the temporal credit assignment problem. Similarly, in chess, a move made in the opening may only prove decisive at the end of the game. This creates a tension between exploitation, using what the agent already knows to gain rewards, and exploration, trying new strategies that might yield even better results. Deep networks fit into this framework by serving as policy networks, mapping states directly to actions. This has enabled breakthroughs like robots teaching themselves to walk and game playing systems such as AlphaGo, which stunned the world by defeating champions in the complex game of Go. Training a deep network is itself a formidable challenge. The process centers on minimizing a loss function, which measures the mismatch between predictions and reality. The standard tool is gradient descent, an iterative method where the network's parameters are nudged in the direction that reduces error. But modern networks can have billions of parameters, making this process daunting. Efficiently computing gradients for each parameter is a massive computational task, and clever algorithms are needed to make it feasible. Even initialization, the choice of starting values for parameters, matters deeply. Poor initialization can lead to vanishing or exploding gradients, stalling learning before it begins. Over time, researchers have developed careful initialization schemes, regularization techniques, and optimization algorithms that make training stable and scalable. Measuring a model's performance is just as important as training it. A network that memorizes training data is useless if it cannot generalize to new inputs. Overfitting remains one of the biggest challenges. The performance of a model depends on the complexity of the task, the amount of training data, and the architecture itself. Hyperparameter tuning is often the hidden labor behind breakthroughs. Choices such as the number of layers, the number of units per layer, the learning rate, and the batch size can mean the difference between success and failure. This process is part science, part art, and often requires extensive experimentation. Neural architecture search, where algorithms automatically design networks, is an emerging field aimed at addressing this complexity. The impact of deep learning extends far beyond the laboratory. In computer vision, it powers systems that can diagnose diseases from medical scans more accurately than some doctors. In natural language processing, it enables translation apps and conversational assistants that understand and respond to human speech. In industry, it drives recommendation engines that tailor content to individuals, autonomous vehicles that perceive their surroundings, and financial systems that detect fraud. Its influence is everywhere, often invisible but deeply embedded in daily life. And yet, its rise is a reminder that technological revolutions often come not from ideas that are safe, but from those once considered unrealistic. The story of deep learning is as much about human perseverance as it is about algorithms. For years, the field survived only because of the dedication of a small group of scientists who believed in an idea few others respected. They wrote papers that were ignored, attended conferences where their talks drew little interest, and continued experimenting even when computing power and data were insufficient. But they also collaborated, mentored students, and built a community that slowly grew. When the world finally caught up, when big data, faster processors, and clever tricks aligned, their decades of groundwork allowed the field to explode. It is a powerful lesson in how science progresses, not always linearly, not always predictably, but through persistence and vision. As we look toward the future, deep learning continues to evolve. Researchers are pushing the boundaries of generative models, reinforcement learning, and architectures tailored for increasingly complex data like graphs and multimodal inputs. The models are growing in scale but also in efficiency as sustainability becomes a pressing concern. And as the technology spreads, ethical questions grow. How should we use systems that can generate realistic but fake content? How do we prevent biases in training data from producing unfair outcomes? These are challenges that require not only technical solutions, but also thoughtful social and policy responses.